I want you to try something for a second. Just hold out your hand, keep it steady, palm up, and just look at it.
Right, just hold it right there in front of you.
Yeah. Picture something passing straight through your hand right now, roughly once every second or two. You can't feel a thing. It isn't sunlight warming your skin, and it isn't the radio waves coming from your phone either. It is a tiny, incredibly fast-moving particle, and it was born a few dozen kilometers above your head.
And, its origins trace back even further than that. That particle is the debris from a very violent collision.
Right.
The original object that caused that collision arrived from deep space. I mean, it might have been launched by a massive star that exploded thousands of years ago or blasted out of some cosmic engine that nobody has ever quite pinned down.
Which is wild to think about.
It really is. But whatever threw it, it crossed the galaxy and slammed into the very top of Earth's atmosphere, moving at close to the speed of light.
And that original incoming piece of space debris is called a cosmic ray. And it is part of this slow, relentless, invisible rain of matter that just never stops. I mean, day or night, rain or shine, it has been striking the planet for its entire history.
Yeah.
You are quite literally being showered by the cosmos right now.
Okay, let's unpack this, because right out of the gate, we have a naming problem.
We do, yeah.
Based on the stack of sources we're looking at for this deep dive, that name, cosmic rays, is a massive historical misdirection.
It really is. It's a remnant from a time when we, frankly, fundamentally misunderstood what we were looking at. The term was coined in the early 20th century.
Back when physicists were just discovering new phenomena left and right.
Exactly. And because of that, they assumed they were dealing with a form of electromagnetic radiation. They envisioned something similar to X-rays or gamma rays, just sort of radiating down from the sky.
So they thought they were dealing with light, essentially, just really high energy light. Right. But these aren't light waves. They are actual physical matter. A cosmic ray is overwhelmingly a single charged particle. We're talking about bare hydrogen nuclei. So protons completely stripped of their electrons and just hurled across the galaxy.
And there's other stuff mixed in too, right?
Yeah, you also get helium nuclei plus a tiny fraction of heavier elements and some stray electrons. But the unifying characteristic is that they have real mass, they carry an electric charge, and they're moving extraordinarily fast.
So they don't just shine on things, they physically smash into them.
Precisely.
Which brings us to how we even figured out this invisible space rain was happening in the first place. Because the 1912 discovery story is fantastic. It perfectly highlights how science often progresses by looking in completely the wrong direction.
Oh, absolutely. Early 20th century physicists had these simple instruments called electroscopes to measure electric charge, and they started noticing that the instruments were slowly discharging in their sealed labs.
Just losing their charge out of nowhere.
Right, exactly. The electroscopes were losing their charge as if an unseen radiation was physically knocking the electrons loose. Naturally, the working hypothesis was that the Earth itself was the source. Scientists assumed this radiation was just, seeping up from radioactive elements in the rocks and soil.
Which makes sense. So the logical prediction was that if you move the electroscope higher up, away from the ground, the discharging effect would weaken.
That was the thought process, yeah.
It's like walking into your house, seeing a puddle on the floor, and assuming you have a leaky pipe in the basement. You start tearing up all the floorboards looking for the source, but in reality, the roof is caving in.
That is a great way to put it. And the Austrian physicist Victor Hess decided to actually test this assumption. He went ahead and strapped his instruments into a hot air balloon.
Which is such a bold move for 1912.
It was. He flew repeatedly, eventually reaching altitudes over 5 kilometers.
Wow.
Yeah, and he even scheduled a flight during a partial solar eclipse to ensure the sun wasn't just acting as some ordinary light source responsible for the effect.
Very thorough. And the data completely flipped the script.
Completely. The data he gathered completely inverted the scientific consensus because the discharging effect didn't weaken as he ascended. It amplified significantly.
So the leaky pipe wasn't in the basement? The radiation was coming down from space itself?
Yes, exactly.
But if the radiation gets stronger, the higher you go, you eventually run out of Earth's atmosphere.
Yeah.
You hit the vacuum of space. So the natural next question becomes, well, what exactly is out there with enough firepower to shoot these massive particles at us?
Right, and to answer that, we have to look at different astrophysical phenomena depending on the energy level of the particle. At the lower end of the energy scale, a good portion of the cosmic rays reaching Earth are actually generated locally by our own sun.
So the sun is throwing particles at us.
Yeah, especially during solar flares. The sun accelerates streams of charged particles outward, and their intensity fluctuates with the sun's regular 11-year cycle.
Okay, so the sun handles the low-energy stuff. But to get the medium-energy galactic cosmic rays, the ones that make up the bulk of what strikes Earth, things have to get a lot more violent. We have to look at the explosive deaths of massive stars.
Supernovae, yes.
Right.
When a massive star exhausts its fuel and collapses, it triggers a catastrophic explosion that flings stellar material outward, plowing into the surrounding interstellar gas. This creates a supernova remnant, which is an expanding shockwave that can persist for tens of thousands of years.
And this is where the acceleration happens. When I was reading the sources, it sounded exactly like a game of interstellar ping pong.
That's a really good analogy, actually.
To have this charged particle that gets caught up in the magnetic fields around this expanding shock wave. But it doesn't just ride the wave. It gets bounced back and forth across the shock boundary.
Right, between the approaching layers.
Yeah, and with every single bounce across that front, it steals a little bit of kinetic energy and speeds up. It just gets whacked back and forth across this massive cosmic explosion, gaining speed for thousands of years, until finally, the magnetic paddles hit it so hard it reaches escape velocity, and it gets flung out into the galaxy.
Physicists refer to that mechanism as shock acceleration, and the observational evidence strongly supports it. I mean, we can detect the specific signatures of radiation we would expect if particles were actively being accelerated in this exact manner inside known supernova remnants.
So what does this all mean? We have exploding stars playing ping pong with atomic nuclei, shooting them across the galaxy. That sounds like the absolute ceiling of how crazy the universe gets.
You'd think so, wouldn't you?
But it's not, because supernova shockwaves, as immense as they are, mathematically run out of steam. Their magnetic paddles simply aren't strong enough to accelerate the most extreme particles we've ever detected.
And now we step into the genuinely puzzling category, which is ultra-high energy cosmic rays. To give you a sense of scale, we are talking about a single subatomic particle, something far too small to see or feel, carrying roughly the kinetic energy in a well-struck tennis ball.
All that energy packed into one single proton. That is terrifying.
It's unbelievable. In 1991, an event was recorded that was so extreme, physicists informally dubbed it the "oh my god" particle. Producing a particle with that much energy requires a cosmic accelerator on a scale that completely dwarfs a supernova.
So if a dying star isn't powerful enough, what is? Who is throwing these interstellar tennis balls at us?
Well, the candidate sources are some of the most violent cataclysmic phenomena in the universe. One strong candidate is active galactic nuclei.
Which are black holes, right?
Right, supermassive black holes sitting at the centers of distant galaxies. They're voraciously consuming matter and blasting out highly collimated jets of plasma at just colossal energies. Another candidate is gamma ray bursts, which are extraordinarily brief, violent explosions tied to the collapse of massive stars or even colliding neutron stars.
But I have to push back here for a second, because if we caught the oh my god particle, why can't we just trace its trajectory backward? Like, just look back at the exact angle it hit our atmosphere and see which black hole or which explosion sits at the end of that line.
I wish we could, but the universe doesn't make it that easy. You have to remember, cosmic rays are electrically charged. Because of that charge, they interact with the weak magnetic fields that thread through interstellar and intergalactic space.
So they don't fly in a straight line.
Exactly. As they travel over millions of light years, their paths are constantly nudged, bent, and deflected. By the time a cosmic ray arrives at Earth, its direction of travel is completely scrambled. It points nowhere near its actual origin.
It's like trying to figure out who launched a pinball by only looking at the very last bumper it hit before falling down the drain.
Yeah.
The information is just lost. But the sources do point out something called the GZK cutoff, which seems to offer a pretty major clue. It acts as a physical limit on how far these ultra-high-energy particles can actually travel.
Yes, the GZK cutoff is a crucial piece of the puzzle. It's named after the physicists who calculated it. And the concept fundamentally relies on the fact that intergalactic space is not a perfect vacuum.
Oh, right.
It is filled with the cosmic microwave background, which is the faint leftover radiation from the Big Bang.
So space is filled with this sea of ancient microwave photons.
Yes. And for an ultra-high-energy cosmic ray traveling near the speed of light, that background radiation becomes a very dense hazard. When the proton collides with the microwave photon, the sheer energy of that collision actually creates a new particle, a pion out of the kinetic energy.
Just following Einstein's E equals mc squared.
Exactly.
The particle is literally converting its own speed into new mass. It's hitting a cosmic speed bump, bleeding off massive amounts of energy with every collision.
Right. The physics dictate that because of these constant energy-sapping collisions, an ultra-high energy particle cannot travel across the entire observable universe and still arrive with all that energy intact. If it reaches us with the energy of a tennis ball, it simply couldn't have been traveling for very long.
Meaning, whatever fired it at us has to be in our galactic neighborhood.
Yeah.
It narrows the search radius drastically.
It really does.
It is wild to think about. But let's bring this journey all the way home. We've traced these particles from distant black holes, navigating magnetic fields, and slamming into background radiation. Let's look at the final millisecond of the journey, which is hitting Earth. Because they don't just float down to the surface, do they?
No, not at all. The arrival is incredibly dramatic. When that primary cosmic ray hits Earth's atmosphere, it triggers what we call an air shower.
An air shower.
Yeah. The primary particle collides with the nucleus of a nitrogen or oxygen atom tens of kilometers up. The collision completely shatters both the incoming particle and the atmospheric nucleus.
It creates a massive spray of secondary particles.
It initiates a massive cascade, yeah. Among that initial spray are short-lived particles called pions. Those pions decay almost immediately into lighter particles, including neutrinos, which are so ghost-like they pass straight through the entire planet without hitting anything.
They're passing right through the Earth.
Right. But the pions also decay into muons. Meanwhile, the rest of the debris from that very first collision keeps rocketing downward, striking more atmospheric nuclei, shattering them and multiplying. By the time the cascade reaches ground level, that one single incoming particle has created a shower of millions of secondary particles spread across an area the size of several football fields.
And out of all that debris, I really want to focus on the muon, because that is the specific particle passing through your hand right now. Muons present this incredible physics puzzle. They are essentially heavy electrons, but they are inherently unstable. They have an incredibly short lifespan. It's like a ticking time bomb falling from the sky with a timer that is set way too short. I mean, even traveling at near the speed of light, a muon created high in the atmosphere should explode and vanish before it ever reaches the ground.
You're totally right. By classical mechanics, it shouldn't survive the trip. The distance is too great for its microscopic lifespan.
Yet we detect millions of them reaching sea level constantly. So how does the time bomb reach the ground without detonating?
What's fascinating here is that the answer is a real-world demonstration of Einstein's special relativity. Because these muons are traveling at speeds extremely close to the speed of light, time itself genuinely passes more slowly for them relative to an observer standing on the ground.
So time dilation isn't just a sci-fi concept. It physically stretches the muon's lifespan.
It does. From the muon's own frame of reference, it lives its standard, incredibly brief life. No extra time has passed for it. But from our frame of reference on Earth, that exact same brief lifetime is stretched out. The muon's internal clock is ticking so slowly that it has plenty of time to cover the tens of kilometers down to the surface before it decays.
The fact that the muon makes it to your hand is tangible, physical proof that relativity is happening all around us.
It's beautiful, isn't it?
It is, but these particles aren't just doing physics tricks. They have real-world impacts. They physically interact with human biology and our technology. Let's talk about the occupational hazards, starting with flight crews, because the atmosphere shields those of us on the ground, but if you fly long haul at high altitudes, you lose a lot of that shield.
You do, and this is especially pronounced on polar flight routes.
Why the poles?
Well, Earth's magnetic field deflects a lot of cosmic rays. But those magnetic field lines funnel inward at the poles, offering far less shielding than you get at the equator. Because of this, flight crews on polar routes accumulate a noticeably higher dose of cosmic radiation.
But they're actually classified as occupational radiation workers in several countries. They're monitored similarly to technicians in a nuclear power plant.
Exactly. Airlines use specialized software to model and track the cumulative radiation exposure for their crews so they can manage their rosters safely. And, this challenge scales up massively for astronauts.
Oh, I bet.
Once you leave the protection of Earth's atmosphere and magnetic field entirely, cosmic ray exposure becomes one of the primary medical and engineering hurdles for long-duration space missions, like, say, a trip to Mars.
And it isn't just our bodies at risk, it's our silicon, too. A cosmic ray can cause a phenomenon in our computers called a single event upset.
Yeah.
And when I was reading how this actually works mechanically, it just completely blew my mind.
It is a really profound intersection of astrophysics and microelectronics.
Basically, a computer chip is made of billions of microscopic transistors, tiny electrical switches holding a charge to represent a 0 or a 1.
Right.
When a secondary cosmic ray particle passes through the silicon of a chip, it can deposit kinetic energy.
Right.
That energy knocks electrons loose in the silicon, creating a sudden microscopic surge of electric charge. If that tiny surge hits the right transistor, it alters the voltage just enough to flip the switch. It literally changes a 0 to a 1.
It does. And most of the time, flipping a random bit of memory is totally harmless. Your laptop might briefly glitch, or maybe a single pixel in an image renders incorrectly and the system just moves on.
Right, no big deal.
But in highly sensitive systems, think aircraft avionics, satellite controls, or even pacemakers, a flipped bit in the wrong line of code can be catastrophic. Engineers actually have to design physical hardware shielding and redundant software algorithms specifically to catch and correct these cosmic ray-induced glitches.
That is wild. Now, there's also a lot of noise online about cosmic rays causing climate change. And I want to tackle this because it's easy to read a headline and jump to conclusions.
Yes, it is.
Let's separate the actual science from the internet speculation here. Can these space particles actually change our weather?
Well, the hypothesis centers on cloud formation. As cosmic rays pass through the atmosphere, they strip electrons from molecules, creating ions. The idea is that these charged ions act as seeds, helping water vapor condense to form tiny aerosols, which eventually grow into clouds.
Okay, so more cosmic rays would mean more clouds, which would reflect sunlight and cool the Earth.
That's the theory.
And the CERN Particle Physics Laboratory actually built a massive controlled chamber to test this.
They did, yeah, in an experiment called CLOUD. And the laboratory results showed that, yes, ionization from cosmic rays can indeed enhance the formation of aerosol particles under highly specific, controlled conditions.
It works.
In a lab, yes. But we must bridge the gap between a controlled chamber and the actual atmosphere. The particles formed by this process in the lab are often too small to act as effective cloud condensation nuclei in the chaotic, dynamic environment of Earth's actual climate system.
So it's a fascinating mechanism, but it's not the secret driver of global climate behavior.
Right. It remains a debated topic, not a confirmed driver.
Got it. So with all these phenomena, from bit flips to time-traveling muons, how are scientists actually studying this? I mean, how do you catch something invisible that moves at the speed of light?
The detection methods span an incredible range of engineering. At the smallest scale, you have cloud chambers. You fill a sealed container with a supersaturated vapor, often alcohol.
Okay.
When a charged cosmic ray zips through, it ionizes the gas, creating a visible, thin trail of condensation along its path. You can actually build one for a high school science class and watch cosmic rays with your own eyes.
It's amazing you can just see it on a desk. But to catch the oh my god particles, a desktop box doesn't work because they are so incredibly rare. You really need scale. The sources mention the Pierre Auger Observatory in Argentina, which monitors an area the size of Rhode Island.
Yeah, the scale is massive. They use arrays of water tanks to detect the secondary particles hitting the ground, but they pair them with specialized telescopes pointed at the night sky.
Wait, why telescopes?
Because when a massive air shower cascades through the atmosphere, the charged particles excite nitrogen gas in the air, causing it to emit a faint ultraviolet fluorescence. The telescopes literally watch the sky glow for a fraction of a second.
Here's where it gets really interesting, though, because if you want to detect the ghostly neutrinos that are produced in these air showers, you look down, not up. And you use a full cubic kilometer of solid ice in Antarctica at a facility called IceCube.
IceCube is a masterpiece of extreme engineering. Neutrinos interact so rarely with matter that you need a colossal target just to catch one. They drilled deep into the ultra-clear ancient glacial ice at the South Pole and buried thousands of optical sensors.
And the mechanism here is incredible. When a high-energy neutrino actually happens to collide with an atom in the ice, it produces a secondary particle, like a muon. But here's the trick. The speed of light in a vacuum is the absolute speed limit of the universe. But light travels significantly slower through solid ice.
Precisely. The newly created particle is ejected from the collision moving faster than the local speed of light in that specific icy medium.
Right.
Just as an aircraft exceeding the speed of sound creates a sonic boom, this particle exceeding the speed of light in ice creates an optical sonic boom.
It emits a faint cone-shaped flash of blue light called Cherenkov radiation, and the sensors in the ice detect that blue flash, pointing all the way back to the particle's origin.
The scale of human ingenuity required to capture these signals is truly profound.
It really is. So let's recap this journey. A physical piece of an atom is forged in the explosive death of a massive star, or maybe blasted from a supermassive black hole. It gets ping-ponged across the galaxy, navigates twisting magnetic fields, bleeds energy crashing into ancient microwave radiation, and eventually shatters against our upper atmosphere. The debris cascades down, stretches the very fabric of time to prove Einstein right, silently passes through your hand, and maybe flips a bit of data in your laptop.
It is a tangible connection between the most violent events in the cosmos and our everyday reality. And, I want to leave you with a final thought to ponder, building directly on the GZK cutoff we discussed earlier.
The cosmic speed bump.
Exactly. If a cosmic microwave background forces ultra-high energy particles to constantly lose energy, it acts as a strict physical boundary. It means the absolute, most powerful, mind-bogglingly energetic, oh my god particles must originate from relatively nearby sources.
Right, they can't travel forever.
They cannot have traveled from the distant edges of the universe. Which raises a very important question. What kind of unseen, unimaginably violent astrophysical monsters are lurking right here in our own cosmic backyard, just waiting to be discovered?
That is a brilliant, slightly terrifying thought to leave on. The next time you're on a long flight and the cabin crew doesn't mention the cosmic radiation because it's just a Tuesday for them, or the next time you look up at a seemingly empty night sky. Remember, the space above us is never truly empty. Every second, a tiny piece of ancient cosmic violence is raining down, passing quietly straight through the palm of your hand. Thanks for diving deep with us.